A three-dimensional plane can be fully defined with three vectors. Those three vectors are, first of all, a position vector of a point contained in that plane, as well as two vectors which are both contained and non-collinear in that plane. So a vector equation of a plane looks like this. R equals to A plus alpha times U times beta times V, where alpha and beta are just two scalar numbers, in other words, two real numbers. Now, another way of writing this would be in component form, which would look like this. Any point on the plane x, y, z equals to the position vector A, so let's say A1, A2, and A3, plus alpha times the vector u, so let's say it has coordinates u1, u2, and u3, plus beta times v1, v2, v3. Now, I'll try as best I can here to make some sort of a generic sketch here. Let's say we have our x, y, and z frame, so I'm just drawing that here. So that would be our x, y, and z. And so in 3 dimensions, let's just say we have some sort of a plane looking like this, and I'll call that plane P. Now what this is actually saying is if we have a point, which I'll call A here, with a position vector, which I'm calling lowercase a, then all we need, once we have that position vector of the point, are two vectors, which I'll call u and v, which are both contained, fully contained in this plane P, and those two vectors u and v mustn't be collinear. So long as we have those three things, we're all good to go and we can fully define the vector equation of a plane. Now let's go ahead and see how it all works. Now to see how the vector equation of a plane really works, let's consider the following. We're going to write down our equation, r equals to a plus alpha u plus beta v. And in this case, we'll say that the position vector of the point on the plane, a, is a equals to 1, 1, 1. And we'll say that vector u, which is contained in the plane, is the vector 1, 0, 1. And the vector v, which is also fully contained in the plane, has coordinates negative 1, 1, 2. Now, if I draw another sort of generic plane here, x, y, and z. So if I just quickly draw my plane, that's my plane P. Now remember, A, the position vector A, just points towards some point on the plane, doesn't matter which one. That's my position vector A. And u and v are vectors which are fully contained inside this plane and are non-collinear. Now what this vector equation is saying is that any point on this plane can be reached by starting at point A and then considering a linear combination of the two vectors u and v. So that could be 2u plus 3v, or negative u plus 0v, or negative 4u plus 25v. Doesn't matter. Any point on this plane P can be reached by going up to point A on the plane and then considering a linear combination of the two vectors u and v. For instance, if we write out our vector equation here in terms of the components or the coordinates of our vectors, any point on this plane has coordinates x, y, and z, and will therefore equal to the position vector A, that's 1, 1, 1, plus alpha times u, so that's 1, 0, 1, plus beta times v, so that's negative 1, 1, 2. Now alpha and beta, as I suggested a minute ago, could take on any value, negative 5 and 10, or 0 and 0, or 1 and 2, or 1 and negative 2, and so on and so forth. Any real number you can think of. So let's make it simple and look at a couple of cases here. Let's say alpha is equal to 1 and beta is equal to 0. Then in this case, the vector equation of this plane would point towards the following point. x, y, z would have would equal to, so 1, 1, 1 plus 1 times 1, 0, 1 plus 0 times negative 1, 1, 2. That would equal to 1, 1, 1 plus 1, 0, 1 plus 0, 0, 0. And we quickly see that in this case, we're referring to the point on the plane with coordinates 2, 1, 2. And that point could be anywhere on the plane. This is our generic plane, of course, but let's say for argument's sake that we just found this point here. Now let's look at another case. Let's say alpha is equal to negative 1 and beta is equal to 2. Then in this case, our vector equation would point towards the following. X, y, z equals to 1, 1, 1 minus 1 times 1, 0, 1 plus 2 times negative 1, 1, 2. This leads us to 1, 1, 1 minus 1, 0, 1 plus negative 2, 2, 4. Now, the first difference here, 1 minus 1 is 0, plus 2 would be negative 2. So our x-coordinate would be negative 2. Then we have 1 minus 0 plus 2. So that's 1 minus 0 is 1, plus 2 is 3. And finally, 1 minus 1 is 0 plus 4 gives us 4. And there we have it. In this case, we'd be referring to the point on the plane with coordinates negative 2, 3, and 4. And so that's how the vector equation of a plane works. Depending upon the values of alpha and beta, we can reach the infinite number of points on this plane P. And there's no limit to how many points there are, just as there's no limit to how many values we can give alpha and beta. And that is how the vector equation of a plane works.